In this second sublesson of basic BGP concepts, we'll talk about inter-domain routing. We'll talk about types of autonomous systems. We'll talk about inter-AS multi-homing, and we'll talk about the BGP AS path attribute. Let's first look at autonomous system types. An AS can be either single-homed or multi-homed. It can also be either a stub or a transit autonomous system. Single homing means that there's only one link to an external peer. Multi-homing means that we have multiple links to one or more external peers. Here's an example of a single-homed autonomous system. AS1 in this illustration has only one connection to an external peer. There's no need for incoming BGP route advertisements because AS1 has no decisions to make about the best paths to external destinations. There's only one path out. A default route advertised internally and pointing to the external peer as the next hop is good enough for reaching the rest of the world. Outgoing BGP advertisements might still be used to advertise internal prefixes to that external peer. However, there's an alternative even for that. The external peer could be configured with static routes to the AS1 prefixes and then use redistribution to advertise those prefixes to the rest of the world. In that case, for this single-homed AS, BGP is not needed at all. A multi-homed autonomous system has multiple links to one or more external peers in one or more neighboring autonomous systems. Here's a few simple examples. In the top two illustrations, AS1 is multi-homed to a single neighboring autonomous system, AS2. In the bottom two illustrations, AS1 is multi-homed to multiple neighboring autonomous systems. Incoming BGP advertisements might be needed here because in these cases AS1 could have to choose among multiple paths to the same external destination. A stub autonomous system is one in which all packets entering the AS are to destinations within the AS, and all packets leaving the AS are from sources within the AS. A transit autonomous system is one in which packets entering the AS might be to destinations in other ASs. In other words, some packets are passing through the autonomous system. BGP is almost always used with transit autonomous systems. In this illustration, AS1 and AS3 are stub autonomous systems, whereas AS2 is a transit autonomous system. So, for example, some packets might have a source in AS3 and a destination in AS1. Or packets might have a source in AS1 and a destination in AS3. But in both cases, the packets are passing through AS2 without having either a source or a destination in that autonomous system. A stub AS might be single-homed or it might be multi-homed, but a transit AS is always multi-homed. The last basic concept for us to examine is the BGP AS path attribute. AS path is one of many BGP path attributes, and you can think of path attributes as enablers of BGP routing policy. We'll look at AS path and some other path attributes in the context of routing policy in Lesson 7. But AS path also enables two key BGP functions, and that's the reason we want to introduce it in this lesson. AS path, quite simply, is a list of AS numbers that describe the inter-AS path to some destination prefix. The two functions of AS path that are fundamental to the operation of BGP are shortest AS path selection and loop avoidance. Let's look at each of these functions in turn. First, the shortest path determination function. In this illustration, we see 6 autonomous systems, and as we go through this example, we're looking at things from a BGP perspective. That is, we're seeing things from an autonomous system level, and we're not looking at the routers that are internal to each one of these ASs. In our example, we'll be watching a 16-bit prefix, 218.54.0.0, which I'm depicting as some internal prefix in AS1. In the first step of the example, AS1 advertises the prefix to its neighbors, AS6 and AS5. As it advertises the prefix, AS1 adds its AS number to the AS path list. It's shown here in brackets. When the routers in AS5 and AS6 receive that prefix, they record the prefix and they also record the AS path attribute. In the next step, AS5 advertises the prefix to AS2. Notice that as AS5 advertises the prefix, it adds its own AS number to the AS path list. The routers in AS2 then record the prefix along with the AS path attribute for that prefix. AS2 in turn advertises the prefix to its neighbor, AS4. Notice again that as AS2 advertises the prefix, it adds its own AS number to the AS path list. AS6 and AS4 advertise the prefix to neighbor AS3, with which both of them peer. Each of those ASs again add their own AS number to the AS path as they advertise the prefix. AS3 now has two different routes to the prefix 218.54.0.0. It's the AS path attributes that differentiate these routes. Notice that one AS path describes a route through AS6 to AS1, whereas the other is through AS4, then 2, then 5, then 1. AS3 will prefer the route with the shorter AS path list. That is, the list with the least AS numbers on it, in this case 6 and 1. So that's BGP shortest path determination. Given multiple paths to the same destination, BGP will choose the path that passes through the fewest autonomous systems, based on the AS path attribute. Now, there are ways to modify that behavior, and I'll cover the complete BGP decision process in Lesson 7. Notice a couple of important behaviors in this example. First, as an AS path advertises the prefix to its neighbor, it prepends its AS number to the AS path list. That is, it adds the AS number to the front of the list. The list of AS numbers then provides a sequential description of the inter-AS path from whatever point you observe the AS path attribute all the way back to the destination. It's also important to note that even though you don't see the routers within the autonomous systems in this example, a router only adds its AS number to the AS path list when it advertises the prefix to a neighbor in a different autonomous system. This will make more sense to you in Labs 2 and 3 when we talk about eBGP and iBGP. Another important behavior to notice in this example is the way the BGP route is built. An AS advertises a prefix to its neighbor. That neighbor then records the prefix, processes it, and then advertises it to its own neighbors, which then repeat the process. Well, that sounds a lot like distance vector, doesn't it? And in fact, it's very similar. BGP is a vector protocol. But because instead of a numeric cost or hop count that describes a distance back to the destination, we have an AS path list that describes a path through autonomous systems back to the destination, BGP is called a path vector protocol rather than a distance vector protocol. And like distance vector protocols, path vector protocols are vulnerable to loops. And that brings us to the second function of the AS path attribute, loop avoidance. In this example, AS4 advertises the prefix 218.54.0.0 to its neighbor AS10. And as usual, it prepends the AS number onto the AS path list. AS10 then records the prefix. and advertises it to its neighbor AS63, again prepending the AS path list. But then AS63 advertises the prefix to its own neighbor AS4. This could potentially be a routing loop because AS4 originated that route. The way BGP avoids such loops is really quite simple. When a prefix is received from an external peer, the AS path is examined. If the receiving router sees its own AS number in the AS path list, it drops the route. In our example, AS4 examines the AS path of the route received from AS63. It sees its own AS number on the list and drops the route. So again, BGP avoids routing loops by dropping routes received from external neighbors if the AS path of the route contains the local AS number.